We will now dive into the world of random variables and discuss how probability extends to a different realm. This lesson will focus on looking at the main definitions of random variable and then specifically go to a specific type of random variable which is called discrete random variable. Before we start, let's have a look at this diagram. So this is a tree diagram that was created to see the probability of getting a 6 if we throw the dice 3 times. So as you can see, it's not a small tree diagram, it's quite big. And the more events we add up, the more complicated it's going to be. But then let's have a look at the calculations. At the end of each branch, you can see the outcome. So the first one would equate to the probability of getting 3 6s, probability of 2 6s, and so on. So I would encourage you to pause and try and find the probability of each one. Or soon enough, you'll notice the pattern. So this is what you'll get. And you can see that there's not a pattern, but you can see repetitiveness happening here. So you can see that the probability of 2 6s is, you have quite familiar numbers. You have 1 6s and the 0 6s and the 3 6s. Basically, if I would like to summarize this tree diagram, I can summarize it by saying, okay, if I'm rolling a dice 3 times, I could either get 0 6s, 1 6s, 2 or 3 6s. So these are all the possible outcomes I could get. And it's normal for a question to say, well, what's the probability of getting 2 6s? So in this case, you would go, oh, I'll just add up this with this with this. So adding them up. Well, why not make it easier? Why not organize the probability of getting a 0, the probability of getting 1, the probability of getting 2 and 3 in a nice table and make it easier for us to see all the probabilities. So this is the slow introduction to how we deal with random variables, discrete random variables. But before we start formally, it's good to start with formal definitions. So what are we looking at when we say random variables? We're looking at probability distribution. So the probability distribution is the study of how probability of random events are distributed. Because the more random they are, even though they are random, you might expect no pattern to show up, but actually we do get some form of behavior that we can predict. There are 2 types of random variables, or 2 types of distributions. We get discrete random variables and continuous random variables. So going back to the definition of discrete and continuous, so it depends on the type of data you have. You can either put them into discrete random variables or continuous random variables. We will study these separately. So today we're going to do discrete, and then next we're going to do continuous, and then later on we will look at specific examples, meaning I will look at binomial distribution, which is an example of discrete, and then we'll look at normal distribution, which is a specific example of continuous random variables. This is a nice diagram just to show you how the distributions are. So when we say distribution, we mean like this visual representation. So if the lines are single lines here, they represent a discrete distribution. So you have a uniform distribution, you have a binomial distribution that we're going to look into, you have a geometric distribution, and then the closer the lines are, it means it's a continuous variable. So we're looking at a normal continuous normal distribution here. We have a chi-square here. So there are so many different distributions in statistics, but we will mainly look at binomial and normal. So probability distribution, it depicts the expected outcomes for a given data. And we have different characteristics for each distribution. We always look at the mean, the expected value, the standard deviation, the behavior, the certain properties. Sometimes all the distributions share a specific property. Some distributions have specific characteristics that we give them the name for, and they're quite useful for real applications. So the main notations you need to know, because we will use these notations in all random variables. So I'm generalizing here. It's not for discrete only, it's for all random variables. So we will continue using our running example of rolling a 6 so that you can make sense of the definition. So a random variable, what do I mean by a random variable? It's the quantity whose value depends on the outcome of the probability experiment. So we use an uppercase letter. It's basically the event that you're looking at. So the main event, that's your focus. So in our starter, the number of 6s obtained when the dice is rolled 3 times, that's what the capital X will represent. It is always fixed and it doesn't change. So every time I write X, it's just a summary of this. How many times will I get a 6 when I roll the dice 3 times? And this is what I'm looking at. So I could get a 0, a 1, a 2, or 3. So what does the 0, 1, 2, and 3 represent? It represents the number of 6s I could get when I roll the dice 3 times. Now, what possible answers will I get from this? What's the sample space? What are the possible options when I roll the dice 3 times and seeing how many the number of 6s do I get? Well, I could either get a 0, a 1, a 2, or a 3. So when I roll the dice, I could get 0 6s, 1 6, 2 6s, or 3 6s. These outcomes are represented by a lowercase letter. So these are the actual measured value which the random variable can take. What are the values that this can take? It can take these small values. So these are all the possible outcomes you could get. Now, if I've set up the definition, but now I want to ask for the probability. So the notation, the probability of a random variable, so the probability of this becoming this. So the probability of X being equal to lowercase x is how we ask for the probability. So the probability that the number of 6s is X. So for example, if I say, what's the probability that X is equal to 2? So I'm asking what's the probability that I get 2 6s when rolling the dice 3 times. I'm not going to write it all, but when rolling the dice 3 times, what's the probability of getting 2 6s? This is what it means. And if I replace it with 0, I'm asking what's the probability of getting 0 6s. And when I replace it with 3, I'm asking what's the probability of getting 3 6s. We can also change the equal sign to inequalities. So I could say what's the probability of X being less than or equal to 2, meaning what's the probability of getting a 0, a 1, and a 2. Now in this specific example it's discrete, but later on when we do continuous you'll realize that you could get infinitely many values. So what's the probability of getting 2 or 1 or 0? So, and I could change the inequality to bigger than. I can make it strictly less than 2, for example. So any inequality in here. So how do we actually start setting up? Do I always depend on a tree diagram? No. As we've talked about before, you can see that I can combine all these probabilities together. So I can summarize the probabilities into a single table. If I say the probability of getting zeros, it's just 125 over 216. So I write that in the table. The probability of getting a 1 is me adding those up. So I have this plus this plus this. So all three added together. And that will give me 25 over 72. You can simplify them or you can keep them as they are if you want the denominator to stay the same. The probability of getting 2 6s would be 5 over 216 plus 5 over 216 plus 5 over 216 to get 5 over 72. And the probability of getting a 3 is 1 over 260. Now, if I start to add all of these up, what do we notice? You can have a go add them up, what do you notice? You should see that you're getting a 1 out of this, which is not surprising because this is the summation of this, which is all the possible events with rolling a 6. So this takes us to an important property of all random variables. Again, we're still not dealing with discrete specifically. All random variables is that the probabilities have to be between 0 and 1, and the probabilities when we add them up have to be equal to 1. Again, you might think, well, that's typical of probability, but we still need to emphasize that it still applies to random variables here. So let's start doing some questions. In here it says the random variable x has the probability distribution shown. Now, so far you'll slowly notice we're just going to deal with discrete values here. So we are slowly in the discrete random variable world, but the properties still apply to all random variables. So if I want to find the value of c, I need to use these properties, which is that the probabilities have to be between 0 and 1, and if I add them up, it should be equal to 1. So for part A, it's just algebra and setting up the equation. So it should be that the probabilities add up to 1. So if I go 7c plus 5c plus 4c plus 3c plus c, it should be equal to 1. And if you solve this algebraically, you will get c is equal to 1 over 20. Okay, once I have that, then I can calculate the probability given in part B. So I need the probability of x being bigger than or equal to 4. Another way of writing that is saying that you need the probability of it being exactly equal to 4 plus the probability of it being equal to 5. Which is, if I substitute the 1 over 20, I get 3 times 1 over 20 plus 5 times, plus the 1 over 20. And that would just be 4 over 20 or 1 over 5. This is a 1 just to emphasize. Alternatively, just so I can explain this, although we don't need it here, alternatively, if I'm looking at the probability of bigger than or equal to 4, it's the same thing as taking the complement of being less than or equal to 3. So notice I need these probabilities, which is the same thing as taking 1 minus these probabilities, because all the probabilities add up to 1. So the probability of being bigger than or equal to 4 is the same thing as taking 1 minus the probability of x being strictly less than 4. Now, strictly less than 4 is the same thing as saying the probability of being less than or equal to 3. Now, this is a very important point, and notation-wise, I'm just using it in this example. We don't need it in this example specifically, but there are some probability questions that will rely on you understanding that these two are equivalent. X strictly less than 4 is the same thing as less than or equal to 3. However, this is only for discrete. We'll talk about how it's different for continuous. So this will be the same as 1 minus probability of x being equal to 3 minus the probability of x being equal to 2 minus probability of x being equal to 1. Okay, so we're subtracting these. Again, we don't need it for this example. We can simply just do 4 plus 5, but it's useful to remember that the complement events still work here. In this example, we don't need to know what the random variable x represents. They just tell you that this is what it is and this is the probability. You just go with it. All right, trying another example, I would encourage you to pause the video and try this out. This time, the probability is given as a function that you have to figure out. If you are struggling, you can at least follow through with what I'm doing with part A, and then you can figure out the part B, C, and D. Alright, so if we set up the distribution, you first need to note your lowercase x. Always use the correct notation that they have in there. So, and then I'm looking for the probability of capital X and X. So what are the possible values X can take? It's 0, 1, 2, 3, and 4. And then what I'm going to do is the probability of X being equal to one of the X's is just me substituting it here. So I will go 1 over k times 0 squared, which is just 0, and then 1 over k times 1 squared, which is 1, and then 1 over k times 2 squared, which is 4, 1 over k times 3 squared, which is 9, and 1 over k times 4 squared, which is 16. So I can simplify this, but then it also says find the constant k. Well, I will use the same property of distribution that I did in the previous example, which is that they should add up to a 1. So if I add all of these up, I get 0 plus 1 over k plus 4 over k plus 9 over k plus 16 over k equals to 1. And if I do the algebra and simplify that, I will get k equals to 30. So now that I know what k is, I can then rewrite this table into the probabilities are now more specifically 0, 1 over 30, 4 over 30. I'll keep them unsimplified so that it's then easier to do some calculations. And then I have 9 over 30 and 16 over 30. You can simplify them if you want to. So that's part A done. Now, if I want part B, which is find the probability that X is less than or equal to 2, so I'm looking for probability of X less than or equal to 2. So that would be the probability of X being equal to 0, X being equal to 1, and X being equal to 2. So I'm very careful about the inequality here. Okay, so I'm including 2. So that would be the probability of taking 0, 1 over 30, 4 over 30, which is just 5 over 30. And again, you can keep it as this or simplify it to 1 over 6 if you want to. Then part C says, so this was part B, part C says find the mode of the distribution. So the mode, again, going back to definition, is the most frequent number. So which possible outcomes appears the most, and that would be 4. So X, that would be the highest value. So it's when X is equal to 4. That would have the highest probability. And then represent the distribution on a vertical line graph. So that means you will represent the X on the X-axis and the probabilities on the Y-axis, and it will give you something like this. All right, so these are our discrete random variables because our data is discrete here. You can practice questions on these before we do more specific ones. So just to emphasize again, these are properties of all random variables. However, we've slowly dived into discrete ever since we began this example, because if your variables are discrete, then we're directly in a discrete random variable. So we're already dealing with this area as part of the lesson. However, the properties such as these notations and this property applies to all random variables and not just discrete. Then we get to more specific things like expected value. So the expected value is the equivalence of finding the mean of a data set. So we find the mean or expected value of a random variable by multiplying each of the possible outcomes with its probability and then adding them all up. It will make sense as we do an example. So the idea behind the mean is that the number you're going to get is the expected value you would get if you run the experiment several times. So let's go back to our example. If I'm looking for the expected value of x, the formula tells you to take the small letter multiplied by the probability and then add them all up. So what we do is we multiply these two together, multiply, 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 all together, and then you add them all up, and that will give you the expected value. So when I do that, I get 1/2. Now, what does 1/2 mean? It means that if I roll this dice, remember the question was about the dice. If I roll the dice a large number of times, I would expect that the average number of sixes I would get would be 0.5, which means I would get between 0 to 1 number of sixes. So I'd be in between getting no sixes when I roll the dice 3 times or 1 6 when I roll the dice 3 times. So that's what the expected value tells you. You can also find it on the GDC if you plot this in L1 and this in L2, and then you do the one variance stat and you take the mean. It's actually the same value. There's more explanation on expected value. You can pause the video and read through it if you want to. So just pause here. And then here it's explaining how if we throw a dice and you actually do a frequency table and you decide to find the mean, and then compare this mean with a theoretical experiment where I actually know theoretically that rolling the dice gives me these values, and I find the expected value of this distribution, you will notice that the expected values are almost the same. So we can establish that if we roll the dice infinitely many times, or as many times as possible, we will be expected to get between the numbers 3 and 4. All right, another practice on what might not be very obvious as a discrete random variable, but it is. So we're looking at this question, pause through it, try and see how random variables is part of this question, even though it's not obvious. Attempt it if you could, and then I'm going to explain how to do it. So the idea here is that there are different ways of getting a key from the bag, but I can easily summarize these methods into a discrete table. So I could either get, if I'm picking the key 2 times, I could either get 0 keys, 1 key, or 2 keys. The way I could get 0 keys is by always picking a coin and then a coin. So a coin times a coin. I could get 1 key by taking a coin and then a key, or, remember, we could look at different options, a key and then a coin, especially that it is not replaced, so the order matters. And I could get 2 keys by picking up a key and a key. So how would I calculate these? You calculate them as you normally would. What's the probability of not getting a key and only getting coins? The probability of getting the first coin is 7/10. The probability of getting the second coin is 6/9. In here, the probability of getting a coin would be 7/10. The probability of getting a key would be 3/9. Remember, the denominator changes because you're not replacing. And then the opposite, the probability of getting a key first is 3/10, and the probability of getting a coin next is 7/9. But I need to add those 2 options. And then for the key, the probability of picking a key first is 3/10, and then 2/9. And then as we did with the 6's question, I could summarize this into a table. So I could get the number of keys, the probability of getting those keys. So with 0, that would give me 7/15. For 1 key, again, I would get 7/15. And then for 2 keys, I would get 1/15. And you can check that the sum of these is 1. Okay, so we do have a discrete distribution here. And then it says find the expected number of keys taken out of the bag. So expected number would be me, so capital X, would be multiplying these together and then adding them up. So that would be 0 times the 7 over 15 plus 1 times the 7 over 15 plus the 2 times the 1 over 15, and that will give me 9 over 15, which is, if we take it into that decimal, 0.6, which means if I repeat the experiment many times, I would expect to get between 0 and 1 number of keys out of the handbag. So practice expected values, understand how it works. These are SL questions that you can practice on, and these are HL questions you can practice on.